All right, this video is going to talk a little bit about how we can use what's called the dot product. Now we know how to multiply vectors by a scalar. So over here on the right, notice that that's one way to multiply. And all the scalar really does is sort of stretch a vector or shrink it depending on the number. So again, if we're going to multiply our vector over here at the left by 3, essentially we just distribute. So 3 times 5 becomes 15. And 3 times -2 would become -6. And we basically just get a vector that's 3 times longer, right? But in the same direction, proportional. If we kind of picture this thing, we went 5, -2. So we had gone, let me redraw that a little bit. We had gone 5 over and -2 down. So we used to have an old vector that was here. But now we're going to go 15, right? And -6. So essentially we made our vector 3 times longer, right? And that's really all the scalar multiple does. Now a dot product, on the other hand, is just another way of multiplying two vectors together. It's not a scalar multiple. We're actually going to take two whole vectors and multiply. And it's a fairly simple process. Notice up top here we've got V1 and V2 that make up vector V, and W1 and W2 making up vector W. And what we're going to do is we're going to multiply the two horizontal components and the two vertical components, and then we're going to add them up. So a dot product is not a new vector, it's just a scalar. Our answer will just be a number, right? So what we're going to do down here at the bottom, we've got 5, -3, and 2, 7. So let's take 5 times 2, and we'll add that to -3 times 7, and basically 10 minus 21, we get -11, and that would be our dot product. We're just going to get a number. We're going to get a scalar of some sort for an answer there. Now that's a fairly simple process, as you noticed. So hopefully finding a dot product seems pretty easy. We can use dot products to do a couple of different things, and we'll talk more about the idea of finding the work behind something in a different video. But one of the things we can do fairly simply with a pretty easy formula here is find the angle between two vectors. Right? So the measurement of the angle between the given vectors, we want to find theta in our picture down below here, right? So we've got two vectors drawn out, right? 4, 3 and 3, 5, and I want the angle between them, right? I want this theta in between the two of them without having to sort of find a resultant in order to find a couple of extra parts and do a whole lot of extra work there, right? We want to just find the angle in between. Well, we can do that simply in one process here. The cosine of theta, the angle in between, will be equal to their dot products. So again, up top, we're going to say 4 times 3 plus 3 times 5 divided by both their magnitudes. So again, we're going to take them both squared. So 4 squared plus 3 squared, add them up and take their square root. And then same thing for the second vector, 3 squared plus 5 squared, add them up, take their square root. So again, we'll say the cosine of theta will equal, well, the dot product would be 12 plus 15, so it would be 27. On the bottom, we're the square root of 16 plus 9 is 25, so basically we're 5. And again, 9 plus 25 would be the square root of 34. So the inverse cosine then, right, of 27 over 5 root 34. Type that smoothly into our calculators, and I'm going to go ahead and do that on the side here. So just give me 1 second. Inverse cosine, again, of 27 divided by, remember to put some parentheses around the bottom, right, 5 root 34. And we should end up with about a 22.166 degree angle, which makes sense. Taking a look at our picture, that doesn't look like the greatest of angles, so a 22 degree angle seems pretty reasonable. Let's do that just a couple more times. We'll do it a little more quickly here though. So again, we've got some vectors set up and we want to find the angles in between them. So again, we're going to say the cosine will be the dot product over the two magnitudes. If we work out those numbers a little bit, you'll notice in this one we end up getting a 0 in the numerator. So really those magnitudes won't matter a whole lot because the inverse cosine of 0, right, 0 over anything is going to be 0, just comes out to 90 degrees. So that also gives us a little bit of a rule, because that bottom part really didn't matter that much. If our dot product equals 0, realize that we have what we call orthogonal vectors, vectors that are 90 degrees apart. Typically we would call those perpendicular, right, in geometry, two perpendicular lines. With vectors we use that word orthogonal. Just means basically perpendicular vectors, they've got a 90-degree angle in between the two of them. Again, we can also have a much more normal sort of problem here. Again, we set that up, dot product over magnitudes. Feel free to pause the video at any point, by the way, and you can always work these out and see if your answers match mine. But again, then we've got our fraction. We're going to take the inverse cosine of that fraction. But because the top wasn't 0, right, we should get sort of a random angle in there, right, a 41-degree angle. And then finally down here at the bottom, same thing. Feel free to pause if you want to find it first. But otherwise, here's my dot product over my magnitudes, negative 20 over essentially what becomes 20. So that is basically negative 20 over 20 is just negative 1, which is 180 degrees then. Inverse cosine of negative 1 is going to be 180 degrees. And if two vectors are 180 degrees apart, or if they would have been 0 degrees apart, we would say that they're parallel vectors. Parallel vectors. Now, one other thing you can notice about parallel vectors is that they're actually scalar multiples of one another. Notice our two vectors over here at the left. If we had taken this bottom vector times negative 4, right? It's in the opposite direction, so again, negative in order to flip that vector around, but 4 times bigger. Well, isn't negative 4 times negative 2 just going to be 8? And negative 4 times our negative 1 would have been positive 4. So again, they're scalar multiples of one another. So you don't necessarily even have to find the angle in between. If you notice they're scalar multiples, right, then you would know immediately that they're parallel. So if the book asked you a question, kind of like this one, just a second here, kind of like this one here, are the given vectors parallel, orthogonal, or neither? Well, what we could look for right away is that, hey, notice this vector times negative 3 is going to be 12i, right? And again, minus 18j. Basically, the top vector is just negative 3 times the bottom vector, and immediately I would say that those two vectors, right, are parallel vectors. They're in opposite directions, right? They're 180 degrees apart. But again, if we drew those two vectors out, they should come out parallel, right? They're traveling completely the opposite directions. I hope that helps you with finding the angle in between vectors, and of course, finding the dot product of two vectors. If you have any questions, talk to your teacher, and have a great day.